Welcome to the solution to the primes. The equations defining the prime number sequence by James Moore, copyright 2014. Leonard Euler was a very famous Swiss mathematician, and he had this to say about prime numbers. Mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers, and we have reason to believe that it is a mystery into which the human mind will never penetrate. The prime numbers have been a fascination for thousands of years, going back as far as Euclid, 300 BC, in his book called Elements. The sieve of Eratosthenes was created in 200 BC, the first time mathematically that they tried to recreate the pattern within the primes. Thousands of years go by, mathematicians throughout history, and for me it started with a library book. So what are prime numbers? 2, 3, 5, 7, 11, 13, 17, and on. Natural numbers that can only be divided by themselves, and 1 with no remainder. These two mathematicians echo so many comments. Among all mysteries, that of the prime numbers is undoubtedly the most ancient and most resistant. When studying the primes, I came across this. If you look at the complexity of the ocean above, the beauty below, the only thing separating it was the clarity in the equations that you will find here. Quotes about the difficulty of prime numbers. The primes have tantalized mathematicians since the Greeks because they appear to be somewhat randomly distributed, but not completely so. The theory of prime numbers. Those who pursue it will, if they are wise, make no attempt to justify their interest in a subject so trivial and so remote, and will console themselves with the thought that the greatest mathematicians of all ages have found in it a mysterious attraction impossible to resist. It will be millions of years before we'll have any understanding, and even then, it won't be a complete understanding because we are up against the infinite. The problem of distinguishing prime numbers from composite numbers and of resolving the latter into their prime factors is known to be one of the most important and useful in arithmetic. I discovered the equations for the prime number sequence 8 years ago, and over the years it's been fascinating, the comments. I'm grateful for them. This one from the teaching chair at the University of Waterloo. I haven't slept for 4 nights. It's magic. This one from Aditya Swarseth. This will shake the foundations of computer science. And then another one from Europe. I have read your proof. It's really impressive and straightforward to read. I'm really impressed with the results of this work. My first reaction when I understood it was, wow. Primes play a huge role in modern cryptography, mainly cryptographic algorithms such as RSA. They're all based on primes. That means that these results can create a revolution in cryptography. And so many other professionals and mathematicians, engineers, etc. over the years, saying beautiful things like amazing, so simple, brilliant. But surely one of my favorite experiences over the years was with Dr. Scott Vanstone. When I discovered the equations that define the prime number sequence, it was brought to the attention of Dr. Scott Vanstone at the University of Waterloo. At the same time, he was also involved with Trust Point Innovation Technologies. His credentials were world-class: PhD in mathematics, a distinguished professor emeritus of mathematics and computer science at the university, 125 patents, authored several books, including The Handbook of Applied Cryptography. He was a Fellow of the Royal Society of Canada Academy of Sciences. He earned the Premier's Award for Lifetime Achievement in Innovation, Fellow of the International Association of Cryptologic Research, and a Canadian Technological Leader Award, Lifetime Achievement. Truly one of the best in the world. My friend, the chair of mechatronics at the University of Waterloo, brought it to his attention, and he said to him, "I haven't slept for 4 nights." I presented my work to Dr. Vanstone, and when I finished, he placed his head in his hands and he looked at me saying, "Do you have any idea what this means?" And I quietly said to him, "Yes, sir, I think I do." Who would have thought that simple multiplication would be so important every day? RSA encryption uses the difficulty of factoring the product of 2 large prime numbers to make sure hackers can't find your credit card number. To implement it, first you must find 2 really large prime numbers and then multiply them together. To begin, we start with the fundamentals. Along with infinity, the beginning, we start with the natural number line. And we introduce you to what we call the fundamental 4. To begin, we'll start with the function 2x. When x equals 0, we get 0. When x equals 1, we get 2. When x equals 2, we get 4. When x equals 3, we get 6. And that continues on to infinity. Then we move on to 3 plus 6x. When x is 0, we get 3. When x is 1, we get 9. When x is 2, we get 15. And then 21, then 27, and on to infinity also. Similarly, 5 plus 6x provides us with 5, 11, 17, 23, 29, giving us the third of the fundamental 4. And lastly, the fourth is 7 plus 6x, giving us 7, 13, 19, 25, 31, etc. Using these fundamental 4, we will obtain the prime number equations. Fascinating is that if you typed in 2x, 3 plus 6x, 5 plus 6x, and 7 plus 6x, like here on the screen, Google has no answer for it. The fundamental 4 do not exist in number theory. Now this is where the fundamental 4 are so important when it comes to prime numbers. Because these 4 equations, when combined, produce every natural number from 2 to infinity in the most efficient manner. This is the most important part, though. When you look at 2, it is the only even prime number. All other even numbers can be factored by 2. Given that 3 is a prime number, and all numbers produced from the equation 3 plus 6x are factorable by 3, 3 is the only prime number that relates to 3. That gives us only 2 options here. 5 plus 6x and 7 plus 6x are all odd numbers. Given that all prime numbers are odd, they must be produced by these equations, 5 plus 6x and 7 plus 6x. Moving further along with utilizing the fundamental 4. Looking at 2x, in light blue, 4, 6, 8, etc. are all factorable by 2, so they are eliminated as possible primes. Looking at 3 plus 6x, in light blue again, 9, 15, 21, etc. all factorable by 3, so they are not prime. But looking at 5 plus 6x and 7 plus 6x, all those numbers are possible. If we eliminate the even numbers and those that aren't associated with 3, we are left with this sequence of numbers. 2, 3, 5, 7, 11, 13, 17, and on. And with that, we are so close. This is a list of prime numbers. 2, 3, 5, 7, and on. Comparing that list with our manufactured list, understanding that 2 and 3 have been established to be prime already, the list of the numbers is almost identical to the primes. And it comes from the equations 5 plus 6x and 7 plus 6x. All other factors created by 2x and 3 plus 6x have been removed. If we could eliminate those that are factorable as shown below in light green, that is 25, 35, 49, 55, etc., we would have it. Going back to our list of primes and what we have, if we consider the light green numbers, if there was some way we could eliminate them, we would have the prime number sequence. Now, way too many late nights on chalkboards. Having established that 2 and 3 are prime already, we need to determine 5 and its role in all of this. And we find that if you multiply 5 by one of the fundamental 4, you get 25, 55, 85. It starts at 25 with a period of 5 times 6, which is 30. If we take that same potential prime, 5, multiply it by one of the fundamentals, you get 35, 65, 95, starting at 35 with a period of 30. Well, what about 7? If we start it on the two fundamentals, 5 plus 6x, 7 plus 6x, we achieve these numbers with these periods. 11. If we remove all of the highlighted light green numbers that were created from possible primes like 5, 7, 11, utilized the two equations that are part of the fundamental 4, we get the prime numbers. The equations defining the prime number sequence. Realizing 2 and 3 are prime by definition, the equations for all possible primes have been proven mathematically to come from 5 plus 6x and 7 plus 6x. These create the possible primes, 5, 11, 17, 23, 7, 13, 19, 25, etc. For each of those possible primes, there are periodic non-primes that are determined and generated by them themselves. We take one of those, a potential prime, we multiply it by one of the fundamentals, and we have a starting point, and then a period at which it continues on, creating elimination values that we need to get rid of in order to get to the prime sequence list. These non-primes, once eliminated, leave only the prime numbers that we have been searching for. Then in celebration, the equations defining the prime number sequence. 5 plus 6x, 7 plus 6x, creating potential primes. From those potential primes, we multiply through each time 5 plus 6x, 7 plus 6x to create elimination values that, when subtracted from the manufactured list, create the prime numbers as you see above. In essence, then, Each possible prime number sends out two elimination signals of unique discrete values and periods derived from each potential prime, eliminating all non-prime numbers and ensuring the uniqueness of the primes. These elimination signals are indeed factors of the original potential prime values, and being factors, they are not primes and are eliminated. Recalling that 5 plus 6x and 7 plus 6x create all possible primes as well as odd non-primes, by using these two equations to create the factors of the potential primes, it ensures that every potential prime value is tested, their factors generated, and then removed from the prime sequence, leaving only prime numbers. For each potential prime number, these two elimination signals combine, with an infinite accumulation of elimination signals acting upon, thinning out, the potential primes, leaving fewer and fewer primes as numbers get larger, and, for the same reason, fewer twin primes. Now this is a bit of fascination. There's two ways of showing the prime numbers. One is through what's called a Dirac impulse in red. They're 1 unit high. But you can also see it in terms of sinusoidal values, kind of like sine waves, where you can see the 5 in blue, 5, 11, 17, and on. And the same with 7 in red. Now what happens is, in elimination, all of those potential primes create a tremendous number of elimination signals. In fact, within a very short time, it looks like this. And within a very short time, it looks like this. There's an interesting question in prime theory that's answered now. But the question is there a single equation that if you put in, say, a number, you would get a prime out? Looking at the complexity of all of the elimination signals, the clear answer to that is no. We then designed computer software for equation testing and verification. A computer program was designed to test and verify the proof of the prime number equations. It was completed one stage at a time, with each stage of programming following standard systems design practices. Each iteration went through extensive testing, including a final runtime of 7 continuous days. All primes generated were exact and verified. This is the opening screen. The first column, array P, references a list of computed and verified prime numbers used in academia for comparison and testing. The second and third columns generate prime numbers using the proof equations. The second column is based on 5 plus 6x, and the third is based on 7 plus 6x, both inclusive of the equations for the elimination values. The values 5, 6, and 7 are input in the boxes on the left-hand side. Pressing Generate Arrays starts the program. The primes are generated, as you see, from the 5 plus 6x, that's the second column, and then 7 are generated from the 7 plus 6x in the third column. The primes generated from arrays from 5 plus 6x and 7 plus 6x are then combined to create the prime number sequence. To complete this, all the prime numbers generated with the software program are compared to the academic values for verification. The zeros on the right indicate a perfect match between the ones generated and the ones used in academia.